Okay, so this is going to be me solving some questions about harmonic motion, and this is what I plan to be the last one in the harmonic motion series. I might in the future come back and do a video on, say, physical pendulums or like springs and more in depth, but I'm not planning on it at the moment. So I'm just going to solve the multiple questions. I chose some questions. I think these are the best ones I could find, at least from the list I was going off of. And we're just going to get started with them, okay? All right. Question number one: a mass of M hangs from a spring attached to a ceiling is at rest, stretched a distance d from the spring's old position. The mass is swapped with one of mass 2m. What is the period of the resulting oscillation? So let's draw this. And because I'm a horrible artist, we're going to just do this really carefully. So this is its normal position. Here is norm. And what it does is it stretches another length. It stretches this length d, and it's relaxed in this position. So I might have drawn this a bit too big. Well, let me see if I can downsize this. I'm not very good with technology though, so I don't know if I can down. I'm just gonna quickly draw it like this. So this is relaxed. This is its position normally. Now we attach mass here, causing its, actually I shouldn't draw like that. So we're going to attach a mass causing it to stretch a distance d. This is d. And this is mass m. Now what we're going to do is we're going to double m, causing it to drop half as low. So it's going to actually end up stretching down to here. But what actually happens though is it's going to undergo simple harmonic motion because it's going to have velocity when it reaches here, causing it to continue falling down another distance d, where it then proceeds to go back up to here, and it's going to be swapping all the way down, like bouncing around this motion. And our question is, what is the period of its oscillation? So how long does it take to go from here all the way down to all the way back up? Okay, well, first we need the period of oscillation for a spring. And you should have an equation sheet for this. If you know, you can also just easily solve for it or remember it. But what we know is though that t equals 2 pi of the square root of m over k. And when you get asked this question, you're likely going to be asked for, I'm going to just write that this is now 2m. Likely going to ask for it in a bit of a different form what's normal. And in this case, the form is going to be a bit weird. You're probably going to get multiple questions which are asking for being the resulting form. But basically what we're going to do is we're going to swap out this k in order to change the form of this answer. Well, first off, we can swap out m with 2m. Over k. Now, what's the k value? Well, what you'll notice here is that it stretched down d and it hit equilibrium. It was at rest here. And what we know is that ma equals mg minus kv. Because the only forces acting on it are gravity, so the mg, and spring, kv. And because it's at rest, that means this part's equal to 0. So we get 0 equals mg minus kv. So kv equals mg. Oh, not kv, kx. Whoops, sorry about that. Kx. And in this case, x is equal to d. So kd equals mg, or k equals mg over d. This is the answer for K. So we're going to go plug in this value in for here to change the form of it to our expected answer. And this becomes t equals 2 pi square root of 2d over g. Okay, I'm probably going to go start doing this a bit quicker because I kind of explained a lot on that one. A lot of these questions are pretty simple. What are the potential energy and kinetic energy of a mass moving system as functions of times? Okay, so what we know is that potential energy is going to be spring energy. So that means U is equal to 1 half kx squared. And for kinetic energy, it's k equals 1 half mv squared. So for both of these with a mass moving system, what is the value that's changing? For here, it's the x. The x value is changing because in a mass moving system, its position is changing. For here, it's the v because the velocity is changing. So what we're going to do is we're going to sub in the equations for x and v relative to time into these values in order to get u of t and k of t. And what we know is we're just going to go with the so what equation you use kind of depends on the context of it. You're going to generally assume that x is equal to a cosine of omega t and v equals minus a omega sine of omega t. This is just based off assuming the starting position. But for the question I took it off of because I did not come up with these questions. I found them and then I adapted them because I'm not sure if they're copyrighted or not. How it was in the original question was that it started at equilibrium at time t equals 0. The t equals 0, it starts at equilibrium. In that case, we use sine instead of cosine for the position because cosine function is graphed like this. Sine is graphed like this. And here is the one where it starts at equilibrium, where the distance is 0. Here, it's starting at its max stretch. Either way, now you can just plug these into here and this one into there, or whatever you get the x and v equations to be. I'm not going to fully expand that out because I don't think you guys need me to do that. Next question. A mass spring system has kinetic energy 4J when the spring is a total length of 0.5 m. When this length is 0.46 m, this kinetic energy is 3J. What's the minimum length of this spring? So I'm not actually going to fully solve this one out because I don't think some of it's just basic algebra. I'm just going to basically explain how you would go about solving this one. So first off, what we know is that if we want the minimum length of the spring, then we can say is that here is the total energy. We can say that the total energy is just 4J because we want it to be as small as possible. So we want the total energy to be as small as possible. And we know that it has to have at least 4J because there's a point where it has 4J of energy. So we're just going to say that this is it at equilibrium. That means that's when its kinetic energy is the highest. Remember, in a mass spring system, something has highest kinetic energy at equilibrium and zero potential energy at those points. And then at the very edges of its motion is where it has the most potential energy and zero kinetic energy. So we can say that the E total is just equal to 4J. We know that E also equals 1 half kx squared plus 1 half mv squared because of, well, these are just two components of its energy, kinetic and potential with potential spring. And what we know is that when it's at a length of 0.46, meaning it's stretched 0.04 meters, its kinetic energy is 3J. So that means E equals 1 half of K times 0.04 squared plus 1 half of Actually, we don't even need this 1/2. What we can write is just replace this with 3 because you know that kinetic energy is 3 at this point. This equals 4. So what we end up getting is that 1/2 k of 0.04 squared equals 1. And at this point, all you have to do is solve for k. And then what you remember is at the very edges of its motion, where it's most stretched, is where it's most stretched, it only has potential energy. So using the solved k for a value, and we know what the max energy is, we can solve for x. Because at when it's most stretched or compressed, it's gonna have just 1/2 kx squared equals 4. And we just have to solve for the x value. And then that's going to give us its max stretch. And then you just have to subtract that from its equilibrium, which we know to be 0.5, in order to get its minimum length. Next question. A physical pendulum is made of a massless rod of length 2r connected by a large ring of radius r and mass m. The period for this pendulum is... Okay. This one's also not very difficult. So remember is that period is equal to 2 pi of the square root of I over mgd. Now, I'm just going to quickly show how you can get to this conclusion, because I think it's kind of like, it's helpful to know. It's not necessary, but I think it's helpful to know. It actually might be necessary. I don't know. It probably is. Yeah, so what we know is, so where this is going to be torque t. I can never remember what way the tau faces. Something like this, I think. Torque equals I alpha. Torque is equal to mg d, where d is the distance to the center of mass, sine theta equals I alpha. This should be minus, by the way. Sine theta can be replaced with just theta. So we got minus mg d theta equals I alpha. And we get that alpha plus mgd over I theta equals 0. And all I just did there was I added this over to the other side divided by I. And this gives, that's based off the basic equation of simple harmonic motion. If you haven't seen this before, this is Newtonian notation, and this is just double derivative. That's also how I first saw it wrote in, so that's just kind of what I write now for when I'm writing this form. This is just the same exact thing as saying this, though. And so this is equal to omega squared. So omega is equal to the square root of mgd over I, and period is equal to 2 pi divided by omega. Anyways, so now all you have to do is calculate I and D. Oh, and also the is M value? No, wait, no. Sometimes you can have more complicated ones where the rod has mass. This is not one of those times, so we don't have to take that into account. Anyway, so we can get is that t equals 2 pi, the square root of I. So the inertia for this, so I should draw this out. This is length r, and this is length 2r. So this is just going to be using parallel axis theorem and the inertia of a ring, a hollow ring. The inertia for that is going to be, I should write the I here. So first it's going to be I of the ring, and that's just going to be mr squared plus what you need for a parallel axis theorem, which you'll notice is it's rotating around an axis that's 3r away from the center. This 2r, and then remember to add in this r here because this inertia is for if it was rotating about a point right here in the center. We are 3r away from the center. So that means it's m times 3r squared. And this just gets you 10mr squared. So the answer becomes 10mr squared over mgd. mg. And for the d now, the center of mass of the hoop is just at the very center of it, so right here, and it's 3r away, so the d is just equal to 3r times 3r. If you do your cancellations and stuff out, this just gives you that it is 10r over 3g. So this is the period. Okay. Next. Okay, here we have two questions. I just combined them because they're really closely related to each other. First, a pendulum is attached to a roof of an elevator. Elevator is accelerating downwards at a constant acceleration of 2/3 g. What is the period of this pendulum in terms of the period of the same pendulum attached to a stationary roof? That's just a bit of a complicated way of saying this. I'm really just asking for if we have a pendulum attached to an accelerating elevator, well, it's accelerating downwards, then what is its period? And I just add the end part because I need something to answer your terms in. So what we know is that the period of a pendulum is the square root, and this is going to be a simple pendulum. We can just say that. It's L over G, I believe. And in this case, if you're in an accelerating elevator, accelerating frame of reference, what's going to change is the gravity. Because remember, all motion is relative. And the gravity relative to you is now different because in your frame of reference is also accelerating. Like, I don't really know how to explain it better than that, to be honest. You're in a falling room, okay? The elevator is falling at a rate of 2/3. Well, it's accelerating down at a rate of 2/3 g. If you were to drop an object in the room now, how quickly is it going to accelerate to the ground of the elevator? I should specify that. The answer is 1/3 g because the elevator is already. It's like elevator is trying to escape the falling object. Elevator is going away at 2/3 g acceleration. The object is falling at an acceleration of g. So that means it's accelerating towards the elevator at a speed of 1/3 g, or an acceleration of 1/3 g. So that all you have to really remember for this one is you have to remember to replace g with 1/3 g, meaning that its period is going to be so meaning for this one its period is going to be 2 pi of square root of L over g over 3. And this gives you 2 pi the square root of 3L over g. And this is equal to the old t, so I'll just write t1 times square root 3. So it's going to take longer because the gravity is now relatively weaker. And just thought as a way to kind of make sense of this is if you were falling and if you were in free fall, you had a pendulum on you, you release it. Do you think that the pendulum is going to start swinging back and forth? No, because everything's falling down right now. In your frame of reference, the pendulum is going to have it's going to have an acceleration of basically 0 because everything around it's also falling. Okay, next. You have a pendulum and spring mass system attached to the roof of an elevator accelerating upwards. What are both of their periods relative to their periods if they were attached to stationary roofs? So this is basically asking the exact same thing, except it's just asking us to basically compare them. So first off, if you're accelerating upwards, what happens? Well, now the ground of the elevator is approaching a dropping object. So I'm going to draw this just to make it easier to kind of understand. So normally this ball is falling to the ground, but now it's accelerating downward. The elevator now is accelerating upwards to approach it, meaning that these two are approaching each other at a very quick rate, quicker than normal. So the relative gravity, the gravity it's basically experiencing is higher because the elevator is accelerating towards it. So yeah, that's how that works. So that means that the new gravity is higher. And if the gravity is higher, then that means the pendulum is going to be, its period is going to be lower because, as we said, period for a pendulum is 2 pi square root L over G. If you increase the G, then that means you're decreasing the period. Okay, next, the spring mass system. What's the period of a spring mass system? Okay, it's m over k. So there's no gravity here, so it's not going to be affected. What will be affected, however, is how low the point of equilibrium will be. Because gravity is relatively higher, that means it's going to hang at a lower speed. It's going to hang at a lower height, I mean. That's the only thing that changing the gravity of the planet you're on or whatever is going. That's the only thing that's going to affect the spring mass system if it's hanging. It's just going to change how low it hangs. It's not going to change the period. Assuming you don't deform the spring, which we're not going to take that into account because that's something dumb. Okay. Let's see how many we're going through. Number 6 out of 9. Okay. You have two blocks moving in simple harmonic motion identically, except block B has a frequency that's twice block A's. What are their max velocities and accelerations? Okay, so for this one, we need to remember that V max equals A omega, and A max equals A omega squared. How do we know this? Because of x equals A cosine omega t, V equals negative A omega sine omega t, and A equals negative A omega squared cosine omega t. So the x max is going to be A, V max is going to be omega, and A max is going to be A omega squared. I should specify that this capital A is a different value than this small a. Small a is acceleration, capital A is just how far the whatever it is moving. It's the amplitude of its motion, the distance it's going. Anyways, so block B has a frequency that's twice block A's. And that means this is going to be doubled, this is going to be quadrupled. If that makes sense. If you don't get that, it's because you're doubling the frequency. So this is obviously going to be doubled because this frequency is now twice what it used to be. And if you're doubling the frequency here, then because it's frequency squared, it's angular frequency squared, then it's going to be quadrupled. Okay, next. A spring mass system is undergoing simple harmonic motion. It reaches a max stretch of d. What is its velocity in terms of v when v is its max velocity? Where v is its max velocity when it's at a stretch of d over 2. Okay. This one might be a bit confusing at first. The way to remember this, though, just comes down to, in my opinion, graphing. I think that's the easiest way to do this, or at least their equations. So remember, we can represent position with a cosine of omega t, and velocity as minus a omega, the sine of omega t. Well, if it is at d over 2, okay, its max stretch is d, so we're going to swap out a with d. Just gonna decrease this eraser size real quick. Okay, so d. Then that means that's cosine of omega t is equal to 1/2. So then the we can start omega t with just theta. It doesn't really matter, just some other variable, because both of these are of omega t. So it means the cosine of theta equals 1/2. Now you can just do arctangent of this. Some of us will have it remembered. I personally have it remembered. I know that this is just 60 degrees or pi over 3 radians. So that means the theta equals 60 degrees or pi over 3 radians. And that means we're just looking for the sine of 60 degrees now. And that's just equal to square root 3 over 2. So that means that the v is square root 3 over 2 v at this position. So the point of this question, in my opinion, is just to emphasize their having sinusoidal equations be their representations. Just remember that you can represent their motion with sinusoidal equations. Because of that, you can come with a lot of cool, interesting questions based off their position. Because we can tell what the omega t is going to be based off the position, that we can just plug that in here. And because we know what sine of omega t is, assuming you remember how it works or use your calculator, you can then come up with some interesting questions. Okay, next one. This is a really simple question. I included this one just in case people didn't know. I think most people get this one, though. Can Cx to the 4 represent the potential energy of an object undergoing simple harmonic motion? The answer to this is just no. Remember, an object's potential energy, if it's undergoing simple harmonic motion, it's closest and all that stuff, is always going to be always going to be a quadratic, not quartic. So just remember, it's going to be Cx squared. So just going to write no. Next. How many questions left? Okay, this is the last one. You have a mass spring system. If you double the spring constant half the distance it stretches, how do their max velocities compare? Okay, well, velocity, remember, equals a omega. If I double the spring constant and half the distance, then what changes? Okay, well, v1 equals a1 omega 1. v2 equals a2 omega 2. What we know is that a2 equals a1 over 2. So we can quickly swap that in there. Now we need to solve for omega 2. Omega 2, okay? What we know is that omega equals the square root of k over m. I've gone over how to solve this in my other video about the basics of simple harmonic motion. But for this one, it's really just using the basic equation. Remember, this one. You should probably be pretty familiar with this if you watched my video, my videos. Oh, that's big unexpected. Oh, well, actually, that's useful. Anyways, so you should be familiar with this equation by now. Square root k over m. So that means the m did not change. But what did change is that the spring constant was doubled. So now this is now 2k1. So this equals square root 2 times omega 1. Because omega 1 is just going to be square root of k1 over m1. This one, you're being multiplied by square root 2. So that means that v2 equals square root 2a1, not square root 2a1, square root 2 over 2 v2, or v1. So that means it's smaller because it's square root 2 over 2 of that. Okay, so those are, in my opinion, some of the best questions I could find off of the study guide thingy progress check I was going off of. And I think I covered basically the majority of the material you have to know. And I don't think there's anything else I really have to say. Most of this unit is just based off of understanding the basics of it pretty well. I don't think there's much stuff that's really like high level. It's just high application of the knowledge, if that makes sense. Anyways, thank you guys for watching. I will see you guys next time.